or we can also start. What is problem? Problem is like this. That better I will start with some basic, then we will go. So as in last class we were discussing about beam element. Beam element. Oh, this is two node element. Okay, two node beam element. So for example, we are having this is our beam element. This is having node one. So did you cover this beam element in your videos? Yes, no. Okay. So this is node one, this is node two, and this element is subjected to any type of loading like this. This is loading. Okay, so this is Qx. Okay, load per meter, Newton per meter. Then each node having 2 degree of freedom. So this node having this will be this B2. Then sorry, it is having only vertical and vertical and rotation degree of freedom. So this will be our P theta 2, and here V1 theta 1. So each node having 2 degree of freedom. Oh, that's fine. And this is having length L. This is having length L and theta 1. Okay. So this is our X coordinate system. This is our Y. Okay. So like initially we were discussing about some isoparametric that mapping. So what I'm going to do here, that I'm going to convert this beam, let's say s equal to 0 here and s equal to 1. Oh, so it will have how, so what will be s? S will be s equal to x minus s x1 by L, where x is the what x is the coordinate in x direction. So what we will get from here, for example, if I want to calculate at x equal to 1, so at x equal to 1, sorry, x at x equal to x1, what will be s? S will be 0. Then at x equal to x2, so this is our x1 at equal to x1, it is equal to x2. So what will be length will be x2 minus x1. Just I'm going to convert from one system to other system. Then at x equal to x2, what will be? S will be x2 minus x1 by L. This is, we already told that this is L only. So S will be 1. Okay. Then similarly, yes, similarly, what will be? ds equal to dx by L. So what we can say? Dx equal to L into ds, like this. So I just converted from like x equal to x1 to x equal to 0 to 1 only. Here, uh, this one, this from x to s. This is not a issue, just I am converting. So now in terms of s, how we can write shape function and other thing. So in terms of S. In terms of S, element goes from 0 to 1. So in terms of S, all the element will be 0 to 1, 0 to 1, like that we have to decide. So what will be like? Just I'm trying. What we I'm trying to do? I'm trying to get shape function for this new mapping system. This one S equal to 0 to 1. This one. So are you getting something? Huh? Okay. So what will be the that trial function, because it is having 4 degrees of freedom. So it is having 4 degrees of freedom. So our trial function will be cubic. So B means like displacement vertical direction. B in terms of S equal to, it will be A naught plus A1x plus A2x square plus A3x cube. So this is in term of S. So in term of S, if I will say in term of X, what will be Bx equal to something A naught plus A1x plus A2x square plus A3x, like this. Similarly, it will be in term of x. Okay. So what will your boundary condition? What will your boundary condition? So uh, here at x equal to 1 or x equal to, or like so. So this is our new element. This is our element x equal. This is s equal to 0 and s equal to 1. Node 1 having 2 degree of freedom. Theta 1, node 2, B2, theta 2. This is node 1, this is node 2. So boundary condition at x equal to 0, Bs will be B1. Okay. Then at s equal to 1, Bs will be B2. And at x equal to s, dv by ds will be theta 1, and that at x equal to 1, dv by ds will be theta 2. These are our 4 boundary conditions. So I will write like this. At s equal to 1, at x equal to 0, then at equal to 1. This will be your boundary condition. Okay. So first we have to put first boundary condition. So this one, 1, 2, 3, 4. This is separate. This is separate. So what first we have to calculate dB by ds. From first boundary condition, from first boundary condition, what they are saying, at x equal to 0, b 0 equal to b1. So what we can say, from by using this boundary condition, what we can say, at x equal to 0, b1 will be e node. Similarly, at x equal to 0, dv by ds will be theta 1, which means that we are going to differentiate. It will be a1 plus, it will be a1 plus 2a2 plus 3a3s. So then it will be out, it will be overall a1 only. So then our what will you get? Theta 2 equal to, sorry, theta 1 equal to a1. Yes, I'm just going to put that. I'm just putting that those boundary condition. Yes, you can say yes or no. It's okay, then fine. Similarly, then second boundary condition. Second boundary condition. What is we having second boundary condition? At x equal to 1, b1 equal to beta 2 and uh, theta 1 equal to theta 2. So what we will get from those boundary condition? B2 equal to B2 equal to A naught plus A1 plus A2 yes. So it will be A naught plus A1. It will be at 1. Sorry. B1 will be A naught plus A1 plus A2 plus A3 and theta at 1 equal to what we will get? We will get A1 plus A2 A2. So A1 plus 2A2 plus 3A3. Okay. So this one we are having B2 equal to A naught plus A1 plus A2 plus A3 and this is theta 2 A1 plus 2A2 plus 3A3. Now from here what we can say, from here add in place of A naught we can put B1. So it will become B2 equal to B1 plus, and in place of B1 we can put theta 1. Okay. I think we missed somewhere. Hmm. Sir, in theta 1 is not only the boundary condition one. Theta 1 is equal to, no, no, there's something I missed there. L should be multiplied by L here somewhere, not theta 1. So wait, it will dx equal to L into ds. So, mm, but we want to find dv. Wait, I will start again here. 1 minute. So, like this is our phase that trial function. It is a node plus a1s plus a2 s square plus a3 s cube. What will be dv by dx? dv by dx will be, oh yes, dv by dx we are going to find dv by dx will be dv by ds into ds by dx. Now that's fine. So what is dv by ds? Something we did here. So what is yes? So from ds by ds, ds by dx, we can say 1 by L. ds by dx. Yes. So dx by dl, we have ds by dx equal to 1 by l. So in place of this, what we can put, and now it's okay. In place of dy, we can put this one. So dv by dx equal to dv by ds into 1 by l. So we miss here boundary condition. So dv by dx, actually what is theta is equal to dv by dx. I have to write here. So theta equal to dv by dx, not dv by ds, not dv by ds, because we are talking about this x coordinate. I think now we got. So we have to multiply here by l only. So this will be this dv by ds. So it will be theta 1 l, theta 2 l. Then this one also will be l, and then dv by what I did. Theta 2 equal to actually what will be by dv by dx. So this dv by dx equal to dv by ds. What we have to find dv by dx? ds a1 plus 2a2 plus 3a3. So a1 plus 2a2s plus 3a3s square into 1 by l. Okay. So at s equal to 1 is at x equal to 1. Array, I got somewhere confused. So can you help me? I got confused. Where I did wrong? This is correct. This is those these are correct only. So okay, this is correct. At x equal to 1, b equal to b1. So this is also okay. This is also okay. And this boundary condition theta 2 equal to a1 plus 2a2 . Hello, can you hear me? So I just okay. Final answer I will write here. I missed somewhere. So what will be a final equal that a1 a2? So we will get a2 equal to, just check, a2 equal to should be minus 3b1 minus 2l theta 1 plus 3b2 minus l theta 2, and a3 will be 2b1 plus l theta 1 minus 2b2 plus l theta 2. So this will be our that a2 and a3. Okay, or a node and a node a1 we already calculated. So what is a node? A node is our B1 and A1 is our L theta 1. So all these get value, all these value going to put, you said something, we will put in trial function. So what we will get? Overall what we will get? Bs equal to 1 minus 3s square plus 2s cube, then b1 plus sl minus 2s square l plus sql into theta 1 plus 3s square minus 2s s cube into beta 2 plus minus ls square plus l s cube into theta 2. Yes. So now in terms of shape function, now in terms of shape functions, what will our displacement vertical direction will be s equal to n1. Okay, tell me how many shape function we will have here. We are having 4 degree of freedom. Hmm? I think right. Okay, so yes, 4 only. So n1, n3, and n4, these are four shape function. There's nodal displacement b1, theta 1, b2, theta 2. So this equation, uh, this equation we can write in this way, and then what will be n1, n2? What will be n1, n2? So n1 will be n1 equal to 1 minus 3s square plus 2s cube. N2 will be sl minus second term 2s square l plus sql. Then n3 will be 3s square minus 2s cube. N4 will be minus ls square plus ls cube. Okay. So this one will be our n1 and this will be our n2. This is n3. This is n4. Okay. Then what is nodal displacement? What is nodal displacement? This is our nodal displacement. Nodal displacement. Okay. So what is n1, n2, n3? N1, n2, n3. This n1, n2, n3. These are the these are the beam ending shape function. Someone calling shape function, someone calling shear function also. So what is actually N1? N1 is the node 1 transfer. This it will represent the this N1 will represent uh, node 1 displacement vertical direction, and N2 represent node 1 rotation in this about z direction. Similarly, N3 and N4. So N1 and N3 represent the translation motion, N2 and N4 represent the rotation motion. So I will write here. So these two will represent translation motion, translation, and these two are for rotation. Hmm. Yes, I think you got some idea what I'm trying to say. So now we will solve one problem that it will be easy to understand. So, oh, you logged out. Okay, so we will solve one problem and it will be easy to understand what actually I am trying to say. So one thing I just want to mention here that stiffness for beam element, stiffness matrix, stiffness matrix for which this is our beam element, node 1, node 2. It is having 2 degree of freedom, V1, theta 2, V1, theta 1. So what will be stiffness matrix? It is having length L. This is length L. So K equal to E I by L cube, A by L cube. It will be 12 6L minus 12 6L, then 4L square 6L 2L square 12 minus 6L, then 4L square. I wrote only uh, one side element, and this will be symmetric. So it will be 4 cross 4 element. Yeah, 4 cross 4 matrix. For this type of element, this is two node beam element. This is two node beam element. Okay, or I will write full matrix also. This is symmetric matrix. So how we write? So it will be like this. So this will be 6L, and then okay, this will be minus 12. This will be 6L. Then this will be 4. Mhm. So 6L. Okay. Then 12. This is 12. This is 12 square and minus 6L. Okay. Then then we will solve one problem that will be easy. One more thing I just want to highlight here. So displacement at any point in the element. What will be range? 0 से लेके between 0 to 1. Okay. What will be our displacement? So this will be BS shape function shape function we already this equation we are going to use. This one only. This equation. So we have to use this equation. Okay. So what will be our shape function? A displacement function that I will copy from here. This one. Copy. Okay. So I will write in terms of shape function. So n1, n2, n3, n4, then b1, theta 1, b2, theta 2. So this is our n1, n2, n3. Sorry, this is our n3, and this will be our n4. So in simple form, how we can write b equal to that displacement vertical direction. It will be 1 minus 3s square plus 2sq. Okay, then l s minus 2s square. Then I will write here 3s square minus 2s Then similarly I will take l common minus s square plus sq and multiply by nodal displacement b1 theta 1 b2 theta 2. So like this we can obtain. So do you have any doubt as of now? Okay. So then similarly bending movement at any point in the element. So bending movement bending movement at any point at any point in the element between 0 to 1. This is our range between 0 to 1. So what will be our bending moment? So m equal to ei, directly I am writing formula, you can drive if you want. Ei minus 6 plus 12s, then l minus 4 plus 6s, then 6 minus 12s, then l. This is in matrix form. Minus 2 plus 6s multiply by nodal displacement. So b1 theta 1, b2 theta 2. Okay. So one more, like we know that bending moment m equal to ei d2 by ds2. Similarly, then b will be ei d2. Then b what will b will be our that's displacement b equal to dm by dx. Okay, so it will be ei d3b by dx3. These are simple, like no strength of material things. I'm just going a little bit fast because it is not required. Oh, this is our that shear function, shear force. Not okay. Yes, shear force or something I missed. This is shear force, so I will this is our displacement only, B. This is shear force. Shear force. So now we are going to solve one problem. Then it will be easy to understand. So you are also feeling what I'm telling you. So okay, one problem. This is problem. This is one of the beam. This problem you have to solve, and this is hinge at this location. क्या हो गई? Oh, sorry, I got disconnected. So this is one of the beam. I will write here. I will draw this beam again. So this is long beam, and this is hinge at this location. At this also, and this here having three location. Fourth one also. This is total four, and we are putting one load here. This is 8 kilonewton. What the dimension? So this is 400 mm. This is also 400 mm. This is 400 mm. So all element having same dimension. So how many node we are having? Node 1, 3, 4. Okay. Yes. So node we are node what we have to calculate, and what is the other parameter. So E equal to 200 gigapascal, and I for this beam element given 10 to the power 5 mm power 4. Okay. Okay, fine. So we have to find deflection, find deflection and shear in a continuous beam shown in the above figure. Okay, so we have to find that displacement shear force in a beam. Okay, So this question we are going to solve. So now first we have to find how many node we are having. So this is our node 1, node 2. This is also one node. So node 3. This is node 4 and node 5. Total we are having 5 node, and each node having 2 degree of freedom. So this is beta 1, theta 1, b2, theta 2. This is having b3 and theta 3. Then b4, theta 4, b5, theta 5. So total 5 degree of freedom. Okay. So from this figure we can see that this is symmetric about this load. This is symmetric about this loading condition. So what we can use, we can use this symmetric condition, and we will we will find that this part displacement and that rotation, and this will be same for this right side also, because this is symmetric. So left side we are going to consider. So now we are going to find solution of this problem. How we are going to solve? Just see. Let's see. Then using solution, using symmetry, using symmetry, only half of the beam, half of the beam can be modeled. How? This is our beam, and this is hinged at this location, and what we will put ruler here, because it is allowed to move in vertical direction, but it is having also zero rotation. So this is our 400 kilonewton force, 4 kilonewton force, because it's a total 8, so it will be 4, 4, 4 both side. Then this is having length 400 mm. This is having length 200 mm. Okay. So now what will be our degree of freedom? How we are going to define? So node, how many node we are having now? 3 node. B1, theta 1, B2, theta 2, B3, theta 3. So total 3 node. Okay, fine. So now what we have to do, we have to find that stiffness matrix for each element. So like this is our first element, this is our second element. So element 1, this is element 2. So both element we have to find the stiffness matrix. Okay, so we will start with first element. First element, what will be first element? As we discussed that for any element, what will be stiffness matrix? This will be our stiffness matrix. This will be our stiffness. Just we have to put value of length and other parameter. So for any element, this will be our stiffness matrix. Okay. So I will just remove this one. Here, given that E equal to 200 gigapascal, L equal to 400 mm, E equal to 10 to power 5 mm power 4. Okay. So what will be in terms of kilonewton? So it will be 200 kilonewton mm per square. Mm square. Yes, fine. So now by putting these all value in this stiffness, so for element first, but stiffness will be K1. So K1, okay. Similarly for second element, similarly, similarly for second element, but only second element we have to take care. The length will be 200 mm because this is our second element. So only length will change, on remain will be, or other thing will be same. Okay. So now we know that for first element we are going to write that equation, force equation. So how we are going to write for first element? So I think I got disconnected. So this problem we are going to solve. Just I am starting this problem. This is one of the beam element. This is one of the beam element. It is having total 1, 2, 3, 4. Total 4 node, and each node having 2 degree freedom, theta 1, that vertical and rotation. So this node having 2 degree freedom. Similarly, this one, this one, this one. And this is from by looking this problem, we can see that we can easily see that this is symmetric about this line. So just we have to model only right left side, and similarly will be that right side will be same. So but we are using this symmetric. Okay. Apart from this, this is given that young modulus 200, and that moment of area moment of inertia. This is having 10 power 5 mm. These are the dimension. So what we have to find the deflection and shear in a above beam problem. Okay. So as I told you, this is symmetric. So by using symmetric condition, only half of the beam can be modeled. So only half beam element we are modeling. Okay. So this is 400, 200. Why we are 200? Because this is total 400. So I divide. So this is 200, 200, and this left side will carry only 4 kilonewton because it is having total 8 kilonewton. Okay. Yes. So now what I did, now for first we have to find the stiffness matrix for each element, element 1 and element 2. So as I told you, stiffness matrix for any two node element that is having only 2 degree of freedom. So this for this element, this will be our ready-made stiffness matrix. It will be 4 by 4. So for each element, just we have to change E, I, and L. So for first element, we are having length 400, and this young modulus 200 kilonewton megapascal, and I equal to 10 to the power 5 mm. Similarly, for second element, hmm,
Sir, that stiffness matrix, no, sir.
hmm,
Sir, in that second row, last fourth column, so it will be like not two, so it will be two, no, sir, 2L square.
let me check my.
And also in
Ah,
the last
yes, yes, yes. It is two only. This is two. This is two, and
so in the last row also. So
this
last
is
row, second row.
this is sorry, sorry, sorry. It's maybe you are not sleeping. Sometimes, like because these are like little bit complex, it's very difficult to remember. So sometimes I also miswrite. Thank you for suggestion. So what I was telling, so this equation that matrix will be same for all the elements. Just we have to change only length and I. So for second element, just we have to take care it is having 400 length. In total we are having 400. We are dividing half and half, it will be only 200. Okay. Till now, okay. So now what we are going to do, we are going to write that we know that F equal to K into some displacement. Okay. So this equation we are going to write. So for first element, K 1 into delta. I'm just writing matrix and force. Okay. So what will be? I will write delta 1 F1. What will be K1? K1 will be after putting value. You will get just put these value in this equation and tell me K1. I'm going to write. You can also calculate with me. So it will be just verify 3.750 minus 3.75, then 750 and 2 10 to the power 5 minus 750 1 10 to the power 5 minus 3.75 minus 750 3.75 7550 this 10 power 5 this 2 10 power 5. Just verify. This will be our that stiffness matrix for first element. Then what will be the displacement matrix? It will be delta 1 equal to B1 theta 1 B2 theta 2. Yes. Mhm. Yes. Then what will be force? So F1 will be R1. 1 minute. No, bro. I'm just taking one class. Can I call after like 30 minutes? Okay, that's fine. So what will be your reaction that it will be then M1 R2 M2. This will be our force M1 for first element. So are you getting same this stiffness matrix or you are getting different?
For same.
Same na? Then if you are getting same, then just verify second also. So for second element, our quad will be K2. K2 will be K2 equal to 30, 3 10 to the power 3 minus 30, then 3 10 to the power 3. 3 10 to the power 3, 4 10 to the power 5, 3 10 to the power 3, 2 10 to the power 5, 30 3 minus 30 over 3, then 10 power 3, and 2 10 power 5, 8 10 power 3, 2 10 power 5. So this will be our that second stiffness matrix for second element. Then what will be theta 2, the displacement 2, delta 2 equal to b2 theta 2, then b3 theta 3. What will be force F2? F2 will be that R2 M2 R3 M3. Okay. So now we have to add these two stiffness to get the global equation, like global matrix. So now what we are going to do, we are going to now we are going to add these above equations. So what we will get to get global equation. So whatever right now we write, these are the local equations. Okay, so we got k, f, delta. So these are in local direction. Okay, now after adding these k1, k2, we will get one global matrix, like global stiffness matrix, global mass matrix, or global force matrix, global that stiffness, that displacement matrix. So what will be our global matrix? K equal to K global equal to K1 plus K2, and delta global equal to delta 1 plus delta 2 in matrix form, and F global equal to. Now you have to get, please tell me what will be your global stiffness matrix. F1 plus F2. So add respected degree of freedom. Only those are sharing we have to add. So from this element we can easily see that this second node sharing this 2 degree of freedom beta 2 b2 and theta 2. So at this node we have to add only. Ah. So are you adding this k1 and k2? What will be global stiffness? Then we will go forward. You want to try or should I write? Okay, to finish. Tell me what will be our global stiffness. So if you add, what you will get?
Hello?
Yes, 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 yes. Tell me, tell me.
Sir, in that video, I'm seeing that's an official innovation. That's the NPTEL section, right? Sorry, the 3.7, right?
And 2250
Yes, sir, 2250,
and 6 10
and
to the
then
power 5.
6 into 10 to the power 5.
That's fine. So I will write here. So what will be our final global that stiffness matrix Kg equal to this. Then what will be size? 3.75 750 minus 3.75 750 0 then 750 minus 3.75 750 0 and 2 10 power 5 minus 750 1 power 5 0 minus 750 and 33.75 2250 2250 and minus 30 300 10 power 5 0 2250 minus 30 3 to 10 power 5 minus 3 10 power 3 okay is equal to 6 10 power 5 minus 3 10 power 3 to 10 power 5 30 minus 3 4 10 power 5. So this will be our uh, how many 6 by 6 matrix. This will be our final global matrix. Then displacement it will be theta delta j equal to theta 1 b1 theta 2 b2 theta 3 b3. Okay. Then force global will be r1 m1 r2 m2 r3 m3. Okay. So now we got this our global mass, sorry, global stiffness, displacement, and force. Now, what we have to do, we have first thing we have to check here what is boundary condition. Boundary condition. Boundary condition. So we will go back again here. We will check what is boundary condition. So boundary condition we are getting from here at this at node 1, node 2, node 3. Okay. So at node 1, vertical distance will be 0 because this is hinge. But okay na? But theta 1 will not be equal to 0. Theta 1 theta 1 will not be equal to 0. Similarly at node 2, vertical displacement will be 0, but theta 2 will not be equal to 0. Similarly 3 at 3 displacement B3 will not be equal to 0 and theta 3 also will not be equal to 0. At 3 displacement will be that what you think at node 3 this will be 0 or not equal to 0. Hello. It will be
They are
0.
not in positive square.
Why?
No, because so that is not the end part. No, sir.
Mm, I think it should be 0 according to my knowledge. I am thinking theta 3. Because, see, at this point, this is symmetric, na? So the slope will be 0 here. It will be like this. If it bend na, it will be like this. So that this slope will be 0. ए, क्या हो गया? Hmm. So at this point, this is symmetric, na? So when that will bend, na, it will look like this. So at this slope will be 0. Actually, what is theta? Theta is the slope of this bending. So the theta 3 will be 0 at this point. Okay. So this will be 0. Theta 3 will be 0. Because it will not be able to resist. Did you get what I am saying? Hmm? Bad connection here today. So this is our boundary condition. So I will just copy the boundary condition from here. These are our boundary condition. So these are our boundary condition. Okay. So now what we have to do, we have to put all together. Then we have to write that f equal to k into delta. This one. And one more thing. So then reaction force R1 at node 1 R1 not equal to 0, but M1 will be 0. R2 not equal to 0, but M2 will be 0. Okay. Then R3 will be minus 4 kilonewton and M will be not equal to 0, it will be M3. So now these boundary condition again we have to take care here. So we will copy this one. We'll copy this one here. So these are the boundary conditions that we have to remember. So um, now after putting boundary condition, this will be F global equal to kg global into delta global. Okay. So I will just copy here this stiffness matrix. This is our F global, copy, and we have to paste here. Okay. This is our stiffness matrix into delta. We are having H delta. Mm, mm, Delta will be 0. Okay, yeah, 1 minute. So it will, I will remove this one. What will be delta? But delta is theta 1, B1, sorry, B1 theta 1, B1 theta 1, B2 theta 2, B3 theta 3, then this one R1 M1, R2 M2, R3 M3. So one thing I want to tell you here, when assembling these to get the stiffness, global stiffness matrix, just we have to add these bottom four coefficient for first element matrix with this first four coefficient. So what we will get, those element we have to add, then what we will get, we will get this type of four element. Mm. This one we have to add only. Okay. So after adding, you will get this. So now by putting this overall, this is our this is our stiffness matrix, displacement force matrix. Hmm. So given that boundary condition defined at B1, B2, okay. So we have to remove respective node and respective row and column. Yes. So what will remain? So we are going to remove. So this one first row, first column. Okay. Then second row, third row, third row, third column, and B3 no, theta 3. So that last row, last row, yes, last row, last column. So what is remaining now? This is also gone. What is remaining now? What will be remaining now? There will be 2, 10 power 5. This one will remain, this one, this one, this one. No, this is good. So this one, mm, this, and this. 10 power 5, then 10 power 5, 0, then again 10 power 5, 6, 10 power 5, minus 3, 10 power 3, 0, minus 3, 10 power 3, then 30 will be theta 1, theta 2, B3 equal to 004 after putting the value. So as of till now you got, should I explain again or you already can understood? Today like having a little bit like bad connection, so connecting and disconnecting again and again. So now by writing the equation, so from what we can write from our matrix, what will be theta 1? It will be that so no need to write this one. Yeah. So 2 10 power 5 theta 1 plus 10 power 6 theta 2 equal to 0 equation 1. Then similar 10 power 5 10 power 5 theta 1 plus 6 10 power 5 theta 2 minus 3 10 power 3 beta b3 equal to 0. Then third equation will be minus 3 10 power 3 theta 2 plus 30 b3 equal to 0. So equation second, equation 3. So now by solving above two equations, we will get theta 1 equal to 0.0008 radian, theta 2 equal to minus 0.0016 radian, and B3 equal to minus 0.2933 mm. This thing you have to verify. This is your homework. Mm. Now, after getting this B1, theta 2, theta 3, so what we will remaining? Theta 1 equal to 0, B1 equal to 0, B2 equal to 0. So we got, and what about, yes, we are having only 6 degree of freedom. So finally we got all these coefficient. Now we are going to find that displacement at a particular location for element 1. So for element 1, element 1, length equal to 400 mm, given that, and note the displacement d means or delta equal to what is that theta 1, sorry, b1 b1 theta 1, okay, b2 theta 2. So we are going to put d equal to what is a b1 is 0, theta 1 we got 0.0008 radian. So I will no need to write dimension here. Then b2 also 0, and theta 2 is minus 0.0016. Okay, like this. I will add transpose, it will become on vertical direction. So now, as I told you, for vertical displacement, we are having one, yeah, this one. This is general equation to get the displacement for any element. So I will just copy from here and okay, copy, then I will paste here down. This will be paste here. Okay. So what will be our displacement for one first element? Here we have everything. So B1, this is our B1, this is our B1, this is our theta 1, this is our theta 2, and this is so B2 and theta 2. Yes. So now finally, after putting this value, what we will get? So B displaced in term of S equal to, it will be 1 minus 3s square plus 2s cube, then L s minus 2s square plus s cube, then This is in matrix form 3 s square 2s cube L minus s square plus h cube. Then this is that 0, 0.0008, then 0 minus 0.0016. This will be our split. So after solving that, what we will get? We will get Vs equal to 0.32s minus 0.32s cube. This will be our vertical displacement for element 1. Just for check, what we can check, if I will put s equal to 0, b equal to b1, and it will be, then what we will get, according to our one, it should be 0. So if I will put s equal to 0 here, what we will get, b as 0 equal to 0. Checking. Similarly, at x equal to 1, b will be b2 and equal to 0. If I will put s equal to 1, we will get again 0. So this is cross check. I think you are getting confused. Similarly, for second element, we have to find for similarly for second element, and that here length will be 200 mm, and nodal displacement, nodal what will be nodal displacement, d equal to that b2 theta 2 b3 theta 3 transpose. So d will be our b2 we calculated 0, but at theta 2 it is minus 0.0016, b3 minus 0. We got 29, theta 3 is 0. Yes. So similar now, again also we are going to use same equation, this equation only. So we have to use this equation again here. So I will copy again, copy. So are you listening or you are feeling bored?
Sir, actually today my network is not good. So will you upload this video on
Ah,
YouTube? So
I also will share this file that whatever I'm writing, so you can check that PDF also. So that what we are doing, I will this will be here. Same function will be same. So b2 theta 2 b3 theta 3, and yes, this is 0 only. So this is our b2 theta 2 b3 and theta 3. So 0 minus 0.0016 minus 0.29330. Then after solving this, what you will get? So if you multiply by 0, so it will be 0. So Bs equal to minus 0.23s minus 0.24s square plus 0.2666 s cube. So this will be displacement for element 2, element 2. Oh, and if you want to find bending moment, so bending moment, how we will find bending moment? What will be bending moment? Uh, as I told you here, what will be bending moment? Yeah, like this will be bending moment. So M equal to EI d2 by dx2. Okay, so by using you can find bending moment and shear force. Shear force B will be what will be B or I will say B equal to M equal to dp by dx. Newton. And so B equal to B will be dm by dx. So our shear force I will say S equal to D or not S. We have to use other good so that it will not mix up. I will write shear force SF. So SF equal to dm by dx and given that dm by dx is 1. So what will be EI d3b by dx3. Right. Like this we have to solve. So okay, for today I think that's enough. If you have any query you can ask. It will be a very long question today be solved. And we start with some basic introduction about beam element. Then I told you how to convert in new coordinate. Then how to find that boundary condition. Then derivation of this A2, A3. Then finally we record this one only. We don't have to learn that much derivation. Only shape function we want. Then finally stiffness matrix for two node beam element. Then how we are going to write that displacement function. Then moment. Then we solve this one problem here. Okay. And we solve this very long problem. Hopefully you got. So I will write here for this is for big 10. It is bigger. Big 10 notes. What is the date today? 27 9 29. This is okay. So if you have any problem, then fine. We can close for today. Next week we will meet. If you have any problem, you can send on that platform. And still we are having only 2 week, only 2 classes. Then we will summarize. Yes. Okay. I will share this PDF with you and you can go through and you can also watch that YouTube and you can subscribe so that you will get update. Fine. We will meet.